Hi, and welcome to the Year 9 Energy Lesson 2. My name's Mrs. McGee and I'm one of the Science Directors, and today we're going to be learning about gravitational potential energy and kinetic energy. Now, before we start this lesson, you will need a paper or an exercise book and a pen. You will also need a calculator, and if you're doing this lesson at home, remember that you need to try and avoid distractions. So put your phone away unless you're using it to watch this lesson, but make sure that you turn notifications off. So here's today's starter. I'd like you to look at this picture of the roller coaster, and for your first question, describe which type of energy is stored in the car at the top of the ride. And question number 2, at the bottom of the ride, this store has decreased. Can you explain which two stores most of the energy has gone to? So you need to think back to what you learned about energy stores and energy transfers in the last lesson. I'm going to give you 1 minute to do the starter. Off you go. So let's see how you did. Grab a different coloured pen and mark your starter. So the first question, the type of energy which is stored at the top of the ride is gravitational potential energy, and this is due to the height of the car above the ground. So question number 2, at the bottom of the ride, the gravitational potential energy has decreased, and it has converted into two stores of energy. These are the kinetic store, because the car has gained speed, it is going faster, and the thermal store due to friction. Now, this thermal store is in the surroundings, so the energy is lost to the surroundings. So here are our learning outcomes for today's lesson. The challenge outcome is to be able to describe the relationship between gravitational potential energy and kinetic energy. And then our aspire outcome is to calculate gravitational potential energy and kinetic energy using two equations that I'm going to teach you. So we're going to start by looking at a simple pendulum system. You will have seen this last lesson if you've done the first video, but it is a really important concept, so we're going to be looking at it again. So here is a simulation of a pendulum. And I'm going to start it going by lifting the pendulum up to one side. And you can see on the left-hand side, you've got some graphs there. And PE is the potential energy, so gravitational potential energy. And you can see that when I've lifted my pendulum up, that has increased the gravitational potential energy of my pendulum. So then I let it go, and my pendulum is swinging backwards and forwards. And if you look at the graphs here, so KE is my kinetic energy, and you can see that the energy stores, KE and PE, so kinetic energy and gravitational potential energy, are continuously interchanging. Now I'm going to slow it down so we can have a look at these graphs a little bit closer. And when my pendulum is here at its highest point, that is where the gravitational potential energy is highest. And at that point, there is almost no kinetic energy at all. If I let my pendulum swing back down, and I'm going to pause it at its lowest point or just near its lowest points there, you can see that now it has got a lot of kinetic energy, so it's moving very fast, but its gravitational potential energy is pretty much zero because it's at its lowest point. And then when it swings back up again, you can see the gravitational potential energy increasing. And then as it swings back down, it decreases, but kinetic energy increases. and you can see that the energy stored in the pendulum keeps shifting from the kinetic energy store to the gravitational potential energy store and then back again. But notice that the total energy here stored in the pendulum doesn't change. Okay, so it just moves from kinetic energy store to the gravitational potential energy store and then back again. So we're going to do a quick quiz to see what you have understood from that simulation. So I'd like you to, on your sheet of paper, just write the numbers 1 to 10 going down. And on the right hand side here, you've got a diagram of a pendulum, and you've got the pendulum in 7 different positions, each labelled A to G, and you just need to use these letters to answer these 10 quick questions. Here we go. So question number 1, where is the pendulum at its highest point? So you just need to write the letter. Where do you think the pendulum is at its highest point? Question number 2, at which points does the pendulum have the most gravitational potential energy? So again, just write the letters. Question number 3, at which point is the pendulum moving fastest? Question number 4, at which point does the pendulum have the most kinetic energy? Okay, ready for question number 5. Question 5, where is the pendulum speeding up? So between which 2 letters, between which 2 positions is the pendulum speeding up? Question 6, where is the pendulum slowing down? Question 7, between positions A and D, how is the gravitational energy store changing? I'll give you a moment to answer this one. So when the pendulum goes from A to D, what is happening to the gravitational energy store of the pendulum? And then question 8, between A and D, how is the kinetic energy store of the ball changing? Okay, get ready for question 9. Question number 9, between positions D and G this time, how is the gravitational energy store of the pendulum changing? And then final question, between positions D and G, how is the kinetic energy store of the ball changing? So as the pendulum moves from D to G, what happens to the kinetic energy store of the ball? Okay, let's get ready to check our answers. So grab a different coloured pen. So question number 1, where is the pendulum at its highest point? That was A and G. So at A and G, the pendulum is at its highest. Question 2, at which points does the pendulum have the most gravitational potential energy? That is also A and G. So when the pendulum is at its highest, that's when it has the most gravitational potential energy. Question 3, the pendulum was moving fastest at point D. And question 4, the pendulum has the most kinetic energy also at point D, because when it's moving fastest, it has most kinetic energy. Question 5, where is the pendulum speeding up? That was between A and D. So as the pendulum moves down, it starts to get faster. Where is the pendulum slowing down? That's as it moves from D to G. Between A and D, how is the gravitational energy store changing? Well, it is decreasing. And between A and G, the kinetic energy store is increasing because it's getting faster. And now the last 2 questions. So question 9, between D and G this time, the gravitational energy store increases because the pendulum is moving back up again. And between D and G, the kinetic energy store decreases because the pendulum is slowing down. So give yourselves a mark out of 10 for this quick quiz. If you feel like you haven't understood it well enough, then you can go back a little bit and watch the simulation of the pendulum again. So this time we're going to look at the effects of friction or air resistance on the pendulum swinging. So if I set my pendulum off again, there we go. So this is what we were looking at before. You can see that the pendulum is swinging continuously backwards and forwards, and that at each end it's reaching the same maximum height. And if you look at the graphs here, you can see that the gravitational potential energy is being shifted to kinetic energy and then back again. And if you look at the maximums for both of them, I'll just slow it down a second. The maximum kinetic energy is the same as the maximum gravitational potential energy, which is then the same as the maximum kinetic energy again. So this is assuming that this is a perfect system and that there are no frictional forces acting on the pendulum at all. Now, in reality, on Earth, that is never the case, because on Earth, this pendulum would be swinging through air. And so there would be frictional forces or air resistance as the pendulum hits the particles in the air that it's swinging through. So I'm going to add those frictional forces to the system now. And you can see straight away that we have got an extra graph here increasing. So that is the thermal energy store. And that is actually the thermal energy store of the surroundings. So that's the air around the pendulum. And you can see that the maximum kinetic energy and the maximum gravitational potential energy of the pendulum are both decreasing. That's because they are losing energy. They are losing energy that is being transferred to the thermal energy store of the surroundings. Now, the total energy in the system doesn't change, but you can see now more than half of that total energy is the thermal energy stored in the surroundings. And now much less than half of that energy is stored in the pendulum itself. And if you look at the pendulum again, you can see that it's now moving slower than it was before because its maximum kinetic energy has decreased, and it's also not swinging as high. So before it was swinging right up to about here, and now it's not reaching anywhere near the same height as it was before. And eventually what will happen is the kinetic energy stores and the gravitational potential energy stores will both decrease right down to zero, because all of that energy will have been transferred to the thermal energy store of the surroundings, and the pendulum itself will stop moving. So on Earth, moving through air, a pendulum cannot keep moving forever because it is losing energy that is being transferred to the thermal energy store of the surroundings. And there we go. I've just sped it up to show you the pendulum stopping once it has no more kinetic energy or gravitational potential energy, because all of it has been transferred to the thermal energy store of the surroundings. Okay, now let's see if you've understood that. This is Neil deGrasse Tyson, and he is an American physicist. And he is holding a pendulum with a really heavy mass at the end of the string, starting right against his nose. And he's letting the pendulum go without putting any force on it. And you can see that when it swings back, instead of hitting him in the face, as you might expect, it just really gently taps him on the nose. Okay, there. So your task is to try and explain why the pendulum will not hit him in the face and why it will not swing forever. So eventually that pendulum will slow down and stop. And I'd like you to try and refer to energy when you are writing your explanation. So I'm going to give you 1 minute to do this. Don't worry if it feels a bit complicated, just give it a go and we'll mark it together afterwards. Ready? Go. Okay, let's see how you did. So grab your different coloured pen. So here are some points that you could have included in your explanation. First of all, when Tyson lets go of the pendulum without pushing it, most of its gravitational potential energy is transferred to kinetic energy. But some of that energy is also transferred to the thermal energy store of the surroundings, and this is because of friction or air resistance. So because of this, the overall energy that's stored in the pendulum actually decreases, and it cannot reach the same maximum height as it actually started at. And eventually what will happen is the pendulum will not have any gravitational or kinetic energy left and will stop. So these are some of the points that you could have included. It's more important that you included some of those keywords that are in bold. So just compare that to your answer. Don't worry if you didn't write this exactly, but take a minute now, pause the video if you need to use this to try and improve the answer that you wrote. Okay, we're now going to look at this transfer between gravitational potential energy and kinetic energy and thermal energy stores in the surroundings. In a different example, we're going to look at roller coasters, but the same principle applies. So you have your roller coaster at the top, the car, sorry, at the top of the roller coaster in position A. And as you know from what you know of roller coasters, the car is going to go down the hill, get to C, and then go back up the next hill to point D. Okay, so think about what we've learned so far about the pendulum, and I'd like you to try and apply those ideas to the roller coaster situation. And I'm going to give you 4 questions to have a go at. Number 1, explain at which point the car has the most gravitational potential energy. Now notice the command word explain, so that means you have to say why that happens. So you might want to use the connective because. Question 2, explain at which points the car has the most kinetic energy. Question 3, describe the change in energy stores happening at point B. And number 4, explain why the peaks of a roller coaster must get smaller. So the first peak is always going to be the highest. Why is that? I'm going to give you 2 minutes to have a go at these 4 questions. Off you go. Okay, 2 minutes are up. Let's see how you did. So first question, at which point did the car have the most gravitational potential energy and why? Well, that was point A, because this is where it is highest off the ground. So the higher the car is, the more gravitational potential energy it has. Question 2, at which point does the car have the most kinetic energy? That's point C because this is where it's moving fastest, at the bottom of that first hill. Question number 3, describe the change in the car's energy stores happening at point B. So at point B, the car is moving down the hill. So the gravitational potential energy store that it had at the top of the hill at point A is decreasing. But at the same time, its store of kinetic energy is increasing as the car is moving faster. And question 4, why is it that the peaks of a roller coaster must get smaller? The reason for this is that as the car moves along the tracks, there is going to be friction, there will also be air resistance. So some of the energy stored in the car is going to be transferred to the thermal energy store of the surroundings. So what this means is that the car's total energy store decreases, so it is not going to be able to climb as high because as it moves along the roller coaster and it's losing some of its energy store, it will never be able to have the same amount of maximum gravitational potential energy as it did at the start, so it will never be able to reach quite as high as it did at the start. Okay, so far in this lesson, we've been focused on our challenge outcome, and we've been looking at how we describe the relationship between gravitational potential energy and kinetic energy. We're now going to look at how we can calculate both of these types of energies. So if we want to learn how to calculate gravitational potential energy, it helps to first think about the factors that would affect this gravitational potential energy. So we've got the example here of a skateboarder in a skate park. And if I lift the skateboarder and put them to the top of the ramp in the skate park, you can see here that the amount of potential energy, so this is the gravitational potential energy, has increased. And if I put the skateboarder back down on the ground, then the amount of gravitational potential energy decreases down to 0 when the skateboard is on the ground. So if I lift them up again, and if I want, I can hover them up in the air, and you can see that the higher the skateboarder is, the more gravitational potential energy, and the lower they are, the less gravitational potential energy. So height is one factor that affects gravitational potential energy. Now, another factor that will affect it is mass. So if I decrease the mass of the skateboarder, so now they're a very small skateboarder, you can see that the amount of gravitational potential energy has also decreased. But if I increase their mass, then you can see that at the same time, the gravitational potential energy has increased. So there are two factors here, height and then the mass of the object. Now, there is also a third factor. I'll just let the skateboarder go. There we go. There is a third factor, and we're going to have to go back to the pendulum for this one. And that third factor is gravity. So if I lift my pendulum up, I'm not going to let it swing this time. I'm just going to lift it up. And you can see that as I'm lifting it, the gravitational potential energy is increasing as we would expect. Okay, so the higher it is, the more energy it's got. I can change its mass, so I can make it really small, decrease the mass, and you can see it has decreased gravitational potential energy. Or I can increase its mass. So I've made the pendulum really heavy, and the gravitational potential energy has increased. But the third factor is gravity. So if this pendulum were in space, so I had 0 gravity, you can see that the gravitational potential energy has decreased to 0 as well. So in space, if there's no gravity at all, then the object will have no gravitational potential energy. And if I press play on my simulation, you can see that the pendulum doesn't actually fall. Now, if I increase the gravity, as I increase it, you can see that the amount of gravitational potential energy also increases. And so now I've given it a lot of gravity, or gravitational field strength it's called, and if I press play, my pendulum is now going to swing. So we can summarize the effect that these factors have on gravitational potential energy using this equation. Now, this is an equation that you need to memorize so that you can use it in exam questions. The equation is EP equals m times g times h, and I'd like you to write this equation down in your notes. So EP is the gravitational potential energy, and it's measured in joules. M is the mass of the object, which is measured in kilograms. G is the gravitational field strength, which is measured in newtons per kilogram, and on Earth, G equals 9.8 newtons per kilogram. And then H is the height in meters of the object. So make sure that you've written this equation down in your books, along with what the symbols mean and the units. Pause the video if you need a bit more time to do this. Okay, so I'm going to do this first calculation and show you what the strategy is, and then you can have a go at some other calculations by yourselves. So in this question, we need to calculate the gravitational potential energy, so the EP, of a 250 kilogram rocket that reaches a height of 190 meters. So the first thing that I'm going to do is write down all the information that is given to me in the question. So EP is what we need to calculate. So we don't know that yet, so I'm going to put a question mark. 250 kilograms, that is the mass. So my mass is 250 kilograms. And I just have a quick check, that is the correct unit for kilograms. And then the height is 190 meters. So my height is 190 meters. And again, meters is the correct unit, so I'm going to put a tick there. Now the next thing that I'm going to do is write the equation that I'm going to use. Now I know that you've already written it, but it's a really good idea to write the equation again to make sure that in the exam you know it and you don't make any mistakes by accident. So EP equals m times g times h. Or just like you do in maths, you can just write it mgh. That means we are just multiplying those three together. So now I'm going to substitute my numbers into the equation. So EP is my unknown, so I'm going to leave it as EP. M, my mass, is 250 kilograms, so I can write 250. I'm going to times it by G. Now G hasn't been given to me in the equation, but we know that it's on Earth, or we assume that it's on Earth, and I told you previously that G on Earth was 9.8, so that is a number that you need to get to know. And then I'm going to multiply it by the height, and the height here given to me is 190 meters, so I write 190. And now I'm going to get my calculator here, and I'm just going to do in my calculator 250 times 9.8 times 190 equals, and I'm going to make sure that I read it correctly, so 465,500. I write my answer here, EP equals 465,500, and I need to add my unit for EP, which is joules, because it's a type of energy. And there you go. So now it's your turn to try some calculations. Here are 3 more questions, and same as we just did together in the first one, for each of these I'd like you to calculate the gravitational potential energy. I'm going to give you 3 minutes to do this. Off you go. So let's have a look at how you got on. Grab your different coloured pen and let's mark this together. So question number 2. Calculate the EP stored in a 50 kilogram student sitting on a chair 0.5 meters above the ground. So let's write down the information that we are given in the question first. So again, EP is our unknown. That's what we're looking for. The 50 kilograms, that's our mass. So the mass is 50 kilograms. And the student is sitting on a chair 0.5 meters above the ground. So that's their height. So the height is 0.5 meters. So let's now write our equation down. It's really important every time you do these questions that you show your working and that you show the whole of your working out, because if in the exam you get the final question, the final answer wrong, if you've shown all your working and some of those steps are correct, then you will still pick up marks. So don't be lazy now. Every time you practice it, show your full working out, and before you know it, it will just be second nature. So let's now substitute our numbers into the equation. So EP is our unknown, so we're going to write EP again because it's what we're looking for. Our mass is 50 kilograms. Our G, again, it's not given, but we're on Earth, so we know that it's 9.8 newtons per kilogram. And then we multiply it by the height, which is 0.5. So calculator, and I do 50 times 9.8 times 0.5 equals 245. So my EP is 245, and the unit for gravitational potential energy is joules. Okay, question number 3. So calculate the EP stored in the same student when they stand on a 1.2 meter high table. So let's write our values down again. So EP is what we're looking for. Now the question says that it's the same student, so that means they have the same mass. So the mass given to us last time was 50 kilograms, apologies. And this time they are standing on a table which is 1.2 meters high, so that's our height. So height is 1.2 meters. And again, you can add G, you know that we're on Earth, so that's 9.8 newtons per kilogram. Quick check of the units given, they're correct, kilograms and meters, so we're good to go. Let's now write our equation. EP equals mgh. Substitute the numbers in. EP equals, the mass is 50 kilograms again, G is 9.8, and H is 1.2. You should be getting used to doing this now. So calculator, and we do 50 times 9.8 times 1.2, which is 588. So my gravitational potential energy here is 588 joules. And for the final question now, calculate the EP stored in the same student on the table, so it's the same height, when they are given a 10 kilogram mass to hold. Now there's a little bit of a trick to this question, so let's see how you did. So EP again is our unknown. Now the mass this time, so it says it's the same student, so that's 50 kilograms for the student, but this time the student is holding a 10 kilogram mass, so you have to add the mass that the student is holding to the student's own mass. So actually this time we're going to use a mass of 60 kilograms. And the question says that it's the same table, so the height is the same as it was before, which was 1.2 meters, and we're still on Earth, so G is still 9.8 kilograms, newtons per kilogram. Okay. So now let's get our, write the equation first. So EP equals M times G times H. So now we're going to substitute the numbers in. EP equals, the mass is this one here, 60 kilograms, that's 60, times G, which is 9.8, times H, which is 1.2. So get your calculator and you do 60 times 9.8 times 1.2 equals 705.6. So this time my gravitational potential energy is 705.6 joules. So this time we want to understand how to calculate kinetic energy, and again it helps to have an understanding of the factors that will affect kinetic energy before we look at the equation. So I've got my skateboarder here again, and this time we've got a U-shaped ramp that the skateboarder is going to go up and down, and I'm going to place my skateboarder at the top of the ramp and just let them go. And you can see that their speed increases, then decreases as they go up and down the ramp. And you can notice that the kinetic energy also increases and decreases. So if I put them back to the top, and I'm going to pause them near the bottom of the ramp, and you can see that their speed is really high there, and their kinetic energy is also really high. And you know this from previous lessons, that the faster an object goes, the higher their kinetic energy, and then the slower they go, the lower their kinetic energy. So that's our first factor, is the speed of the object. Now, the second factor I will show you here. So if I let the skateboarder go and pause them again at the bottom of the ramp, where they're going at their fastest, so lots of kinetic energy. If I change the mass of the skateboarder and I make them really small, you can see that their speed hasn't changed, but their kinetic energy is now much smaller than what it was before. If instead I make the skateboarder really big, so I increase their mass, again their speed hasn't changed, but their kinetic energy has increased. So mass is the second factor that will affect the amount of kinetic energy that a moving object has. So here is the equation for calculating kinetic energy, and you can see that it includes the two factors that we have just discussed, mass and velocity. But this equation is a little bit more complicated than the gravitational potential energy equation. I'd like you to write this equation down in your notes, please, again. So it's EK, which is kinetic energy, equals half times mass times velocity squared. So your velocity is the speed of the object in a given direction. So EK is the kinetic energy, which is measured in joules. M is the mass, which is measured in kilograms. And V is the velocity, which is measured in meters per second. Now, one of the tricky things with this equation is that you have to remember that the velocity is squared. So it's just velocity times velocity. But the other tricky part of this equation is that it has this half here. So I'm going to give you a little tip, which is that when you are doing this calculation, instead of typing in half, just use the decimal 0.5. Okay, so 0.5 is the same as half, but it's much simpler if you use that when you're calculating. So pause the video if you need to make sure that you've got this equation written down in your notes along with the units and this tip. Now, just as I did with the previous equation, I'm going to model this first calculation question. The kinetic energy equation is a little bit more complicated than the one for gravitational potential energy, but if we just follow the same strategy, there's no reason why you can't do these calculations really easily too. So if we read the question first and pull out the data that we have from it. So it calculates the EK of a 2 kilogram ball moving at 5 meters per second. So we need to find EK. So that's the kinetic energy, that's our unknown. So I can put a question mark there. The ball has a mass of 2 kilograms. So our mass is 2 kilograms. And that's the correct unit. And you can also write down, if you want, that the unit for EK is joules because it's energy. And the ball is moving at 5 meters per second. So that's the ball's velocity. So my V equals 5 meters per second. And again, that's the correct unit. So now I'm going to write my equation down. EK equals half times M times V squared. Okay, so just like in maths, if we just have letters like this next to each other, it means that we're multiplying them. So ek equals half times m times v squared. So now I'm going to substitute my numbers in. Ek is my unknown, so I'm just going to write ek again, equals, now this half, remember I said that for your calculation you can use the decimal 0.5 because half equals 0.5, and this makes it easier when you're putting it into your calculator, times the mass, which is 2 kilograms, so times 2, times the velocity squared. So my velocity is 5, so I have to do 5 squared. Okay, now this is the tricky bit that you need to be careful with. If you want, you can just write this out as 5 times 5, because that's what 5 squared is, or you could work out using your calculator what 5 squared is first. So you just do 5 times 5 in your calculator, or 5 squared, and you would find that it's 25. So you can do that. You could do ek equals, leave the rest as it is, 0.5 times 2 times 25. And use your calculator to work that out if you don't know it. So now I've got a nice straightforward multiplication. Get your calculator. So it's 0.5 times 2 times 25, which is your 5 squared, equals 25. So in this question, my kinetic energy is 25 and my unit for energy is joules. So now it's over to you. I'd like you to try these 3 calculation questions by yourselves. In each case, you're calculating the kinetic energy of the object. Use the same method that I've just shown you, and I'm going to give you 3 minutes to do this, and then we'll mark them together. Ready? Off you go. So let's see how you got on with these questions. So in question number 2, you need to calculate the EK stored in a 60 kilogram person walking at 1.5 meters per second. So again, we are looking for EK, which is our unknown, and we know that it's energy, so the unit is going to be joules. The 60 kilograms, that is the person's mass. So the mass is 60 kilograms. And then the person is walking at 1.5 meters per second, so that's their velocity. So the velocity is 1.5 meters per second, and those are the correct units there. So let's write the equation. EK equals half times mass times velocity squared. So again, we need to remember to square the velocity. So that's EK equals 0.5 is my half, times the mass, which is 60, times the velocity, which is 1.5, but don't forget to square it. So times 1.5 squared. So if you know how to use your calculators really well, you should just be able to put that sum into the calculator. So 0.5 times 60 times 1.5 squared. Okay, and your calculator should correctly work out that my kinetic energy is 67.5. So my EK equals 67.5, and my unit for kinetic energy is joules. Okay, so now let's do question number 3. Calculate the EK stored in a 60 kilogram person running at 3 meters per second. So this time it's the same person with the same mass, but now they have started running. So again, I'm going to write out what the question gives me. So EK is my unknown, and the unit for kinetic energy is joules. The mass of the person is 60 kilograms. And they're running at 3.0 meters per second, so that's their velocity. Velocity is 3, you can write the 0.0, you can just leave it, meters per second. So now I write my equation. Remember, you need to show you're working out, and you need to get into the habit of doing that. So EK equals half mv squared. Substitute the numbers in now. EK equals 0.5 times the mass, which is 60, times the velocity squared, which is 3 squared. Get your calculator. 0.5 times 60 times 3 squared equals 270. So for question number 3, the kinetic energy is 270. Don't forget the unit, which is joules. And now for the final question of the lesson. So question number 4, calculate the EK stored in a 60 kilogram person riding their 10 kilogram bike at 6 meters per second. So again, this last question, there was a little bit of a trick there. So let's see what the question gives us. So EK is what we're looking for. That's our unknown, and the unit is joules. Now the mass, it's the same 60 kilogram person. So we've got our 60 kilograms, but this time they're riding their bike, and their bike weighs 10 kilograms. So we need to add that 10 kilograms from the bike to the mass of the person, because they are moving together. So they are moving as if that they were one object with one mass. So our total mass is actually 70 kilograms in this question. So that was the trick. And then they're moving at 6 meters per second, so that's our velocity. So V equals 6 meters per second. So now let's write the equation. EK equals half times mass times velocity squared. We'll substitute in the numbers. EK equals 0.5 times the total mass, which is this one here, 70, times the velocity, which is 6, and don't forget to square it. Let's get your calculators out. So 0.5 times 70 times 6 squared equals 1,260. So the kinetic energy of the person and their bike moving together is 1,260 joules. Okay, we're going to leave it there for this lesson because you've actually done quite a lot today. So just a reminder, our challenge outcome for this lesson was to describe the relationship between gravitational potential energy and kinetic energy. And then in the second part of the lesson, our Aspire outcome was to calculate gravitational potential energy and kinetic energy. Now here are the key learning points from this lesson. If you feel that it will help you, you can add this summary to your notes.